Welcome! In this lesson, we build an intuitive picture for how rivers respond to active tectonics. We will connect three ideas. 1. The stream power law that links incision to drainage area and slope. 2. How uplift creates nick points that migrate upstream. And 3. How drainage networks reorganize through river capture and how terraces record uplift. Let's start with the physics in one compact equation. This is the stream power law. E equals K times A to the M times S to the N. Here E is incision rate, K is erodibility and climate, A is drainage area, and S is channel slope. In steady state with uplift U, rivers tend toward E equals U. Solving for slope gives S proportional to the quantity U divided by K times A to the M, all raised to the power 1 over N. This means for higher uplift, channels must steepen, especially where contributing area is small. Geomorphologists often write slope as S equals K S times A to the minus theta, where theta equals M over N. The normalized channel steepness K, S, N correlates with uplift. High K, S, N often flags rapid rock uplift zones. Now let's visualize a river-long profile crossing an active fault. Initially the river is smooth. A sudden uplift along a fault creates a sharp break in slope, a nick point at the fault. Downstream steepens and incisors to the new base level, while upstream retains the old gradient. Over time, the nick point migrates upstream like an erosional wave, steepening the whole profile. These transient nick points are powerful markers of active tectonics. Active tilting and uplift can reorganize drainage. Here are two neighboring basins divided by a ridge. Headward erosion lets one stream cut across the divide and steal flow from the other basin. This is river capture or piracy. A chunk of catchment area transfers, sometimes tens of square kilometers, and flow directions can even reverse upstream. This leaves the landscape in a transient state with migrating divides and upstream moving nick points. Rivers and active belts also build flights of terraces that record incision and uplift. Imagine a valley cross section with former floodplains perched above the modern channel. By dating terrace treads and measuring their heights, we infer incision rates matching uplift on active structures. Along the Himalayan front, late Holocene terraces record 10 to 15 millimeters per year of uplift and incision, among the fastest on Earth. Remote analyses complement field work. Morphometric indices help map active segments. High normalized channel steepness KSN and high stream length gradient often coincide with rapid uplift. Basin asymmetry, mountain front sinuosity, and valley floor width to height ratios discriminate active fronts with narrow V-shaped valleys from inactive broad valleys. A few regional snapshots illustrate these concepts. Himalayan front, very steep rivers, frequent nick points, terraces recording 5 to 15 millimeters per year incision. Andean foreland, mixed capture and antecedent reaches with episodic uplift. European Alps, post-glacial rivers with paired terrace flights and slower incision. Southern Alps, New Zealand, extremely steep, high sediment pulses after earthquakes with rapid adjustments. To summarize, rivers steepen to match uplift, as captured by the stream power law and the steepness index. Uplift creates transient nick points that migrate upstream and record tectonic forcing. Drainage networks reorganize through capture and divide migration under tilting and uplift. Terrace flights and morphometric indices together let us reconstruct uplift histories on 1,000 to 100,000 year timescales.